So what was your conjecture?
I thought that when you take a polytope in 4 dimensions that has f facets and O of f squared vertices, that can happen in 4D.
Right.
When you project it to 3D, by just dropping one coordinate, you see a 3-dimensional polytope. It might still have O of f squared vertices.
Right.
And then if you project that to 2D, like look at its shadow, you see a polygon.
Right.
I thought that 2D polygon would always turn out to have at most O of f vertices, like most of the vertices of the 4 polytope would have to project to the inside of the polygon.
But that was wrong.
Yeah, it turns out you can construct a counterexample using a product polytope.
A product polytope?
Yeah, the cross product of two 2D polygons. You put the 2 polygons in 2 orthogonal subspaces of R4.
So one is in XY and the other is in ZW.
Exactly. Both polygons have n vertices, say 10. We see different shaped polygons in different projections from R4. When the yellow one just projects to a single point, we're looking right down on the pink one.
Okay.
Now for every point in the pink polygon, fill in all the 4D points whose other 2 coordinates fall in the yellow one. This gives us a 4 polytope. Different projections look like different 3 polytopes.
So what's the structure of this thing in 4D?
I'm so glad you asked. Each facet on the boundary is a 3 polytope. It looks like a cylinder because it's the cross product of one whole polygon with an edge of the other.
So there's 2 n facets because the 2 polygons had 2 n edges altogether.
Yeah, right. To see the way they fit together, we can look at just the edges of the polytope with some of the 2-dimensional faces.
It looks like a torus. Those rings, they're copies of the original n-gon?
Right. Each one is the cross product of one of the polygons with a vertex of the other. Notice that every 4-dimensional vertex lies in one of those rings.
So there's your n squared vertices, n rings with n vertices each.
Right. In this projection, the yellow facets fill in the torus with cylinders, and the pink ones fill in the hole.
Hey, we have all the vertices on the boundary of that projection.
Yeah, but it's not that interesting because they all project to the same n vertices. To get the projection to have n squared sharp corners, we're going to have to deform the 4 polytope. We will tilt the yellow facets in 4D so that they won't be parallel to the z-axis anymore. We'll tilt them alternately towards or away from the positive z-axis. So now the edges between them on the outside look like a zigzag. This tilting shrinks alternate edges of the top pink face and the opposite ones of the bottom pink face. And now, when we look straight down, we can see the zigzag edges bounding the yellow faces. The structure of the faces and how they fit together,
The combinatorics?
the combinatorics stay the same. You still have that set of rings that contains all the vertices.
And now in that straight down projection,
Right, the rings project to the zigzag edges.
but you still don't have n squared sharp corners, they're all inside the long edges.
Aha, but if we change the projection just a little bit, scooting the viewpoint in from infinity, the rings open up, and half the vertices in each ring show up as corners on the boundary.
Wait. Oh, right. Changing the projection is just the same as doing a projective transformation of the polytope. So that's it. You've got a polytope with 2 n facets projecting to a polygon with about n squared over 2 vertices.
That's the counterexample.
Huh. What if you take a random projection of, say, the worst possible 4D polytope? How many vertices would you expect on the projection?
Open question. I conjecture 42.